Looking at Chapter 2, Standards for Measurement. So to remind you what a measurement is, it is a quantitative observation, which means that it has numbers and it has units. So for example, 6 inches or 25 meters, something like that is called a quantitative observation. Now, when we work with measurements, we oftentimes have to use scientific notation. Scientific notation is used because numbers are either very, very small, meaning they have a negative exponent, or they're very large, which means they have a positive exponent. So the way that we write them is one number, I'm going to put a number sign, a decimal place. You put the rest of your numbers, I'm just going to make those X's. And then you do a times 10 to the and an exponent, which is either positive or negative. So let's do an example. So 2,468, I want to remind you the decimal place, even though it is not shown, is at the end of the number. So we see how many hops we have to make to get that to be between the first and the second number. So I'm going to go ahead and write that as 2.468 times 10 to the, and we moved 3 spots, so therefore it is to the third power. Now, the opposite here is true for the one that is below. We see that this number is less than 1, so we know our exponent is going to be a negative number. Our decimal place is here. We're going to move 1, 2, 3, 4. So 1.23 times 10 to the negative 4th power. Okay, so you have to know how to write those, put them in scientific notation, and take them back out. Let's do a couple more examples here. So we see here $25 million. So to put that in scientific notation, I would first write that full number out. So that is 25 with 6 zeros. I want you to remember that the decimal place is at the end if you don't see it. So I'm going to write that as 2.5 times 10 to the, and then I'd count over how many, we call them bunny hops, it would take to get between the 2 and the 5. It would take 1, 2, 3, 4, 5, 6, 7. So it would be 2.5 times 10 to the 7th. And since it is dollars, we will put a dollar sign. Let's go ahead and do the one across. So we would get the decimal place to be between the first and the second digit here. That would be 4.867 times 10 to the negative 4th. And again, it's a negative because this number is less than 1. All right, so we're going to put these in actually the opposite, which is decimal notation. So this is a positive 7 exponent, meaning the number is very large. So I'm going to move this decimal place over 7 spots. So that number becomes 602 with 5 zeros. And again, you can always check your work because remember it's at the end. So you'd count over 1, 2, 3, 4, 5, 6, 7. If it ends up being that original answer, you know you did it correctly. Now this last example here, we see the negative 3. So therefore we know the number is less than 1. So I'm going to move the decimal place over 3 spots. That gets a 0.0010 as the number in decimal notation. I always like to put a 0 in front. It just makes it a little bit more of a complete number. All right, measurements and uncertainty. So when you make a measurement, the last digit is the number that is your uncertainty digit. So for example, if you're using a ruler or something like that, that last decimal place you always need to estimate, right? Because it's so small. So we call that the uncertainty digit, and we're going to learn how to take those numbers into account when we do calculations. So the last digit is usually said to be uncertain unless otherwise stated. Here's a little note when we do labs. Always write every digit shown on the balance sheet. No matter what, if it's shown on the balance, you write it on your data table. All right, the next topic here is significant figures. This gets a little bit confusing, so please don't hesitate to look at other YouTube videos that I have linked in the same folder to help explain significant figures. So let's go over the rules that will need to be memorized. So what is a significant figure or a sig fig? It's basically what are the most important digits, okay? They help us make measurements. They help us make decisions when we're doing counting. Okay, so all non-zero digits are always significant. Okay, so what we're going to learn how to do is count how many sig figs. So in this first example, 1,276, I always count any non-zero digit is significant, therefore there are 4 SFs or sig figs in that number. Second rule, all zeros between non-zero digits are significant. Okay? So for example, once you start counting, you do not stop, especially if there are non-zero digits in between. So this 7 is significant, the 0, the 6, the 0, the 7. So all 5 are significant because they are flanked on either end by non-zero digits. All right, third rule, zeros after the decimal point when you have a 0 to the left of the decimal point are not significant. I know that's a little bit confusing, so let me give you an explanation. So since there are no non-zero digits here in the front, these zeros are not significant. That doesn't mean you don't write them. It just means when you count them, they're not considered a significant digit. So the number doesn't change, but the number of sig figs does. So therefore, 1, 2, 3, 4, 5, 6. Why is this 0 significant in the middle? It's because it's flanked on either side, which is described to you in rule number 2. So the only significant digits here are the 8, 3, 2, 4, 0, 7. Rule number 4, zeros after the decimal point, when you have a non-zero to the left of the decimal point, are significant. Okay? So this is, again, zeros are the confusing part of sig figs. So these are called end zeros, and since there is a decimal place right here, this is significant. So therefore, 1, 2, 3 sig figs. Now I want you to compare this number to the next example's number, which is 1300. Okay, let's read that rule and then we'll compare. Zeros at the end of a number when there is no decimal point are considered not significant. So because there is no decimal place here, these are not significant. Okay, so the only significant numbers here are the 1 and the 3. Compared to the previous example, when you see the decimal point, that is significant. Okay, so it's all about significant numbers in regards to decimal places. Now the last one is exact numbers or countable have an infinite number of significant figures, an infinite number of significant figures, okay? So anything that has a unit that is not measurable. So for example, this has chickens, if it said cars, if it said pennies, if it said folders, paper, any of that. If it's a certain number of it, you actually put the infinity sign or you can write infinite. Okay? Sig figs in calculations. So when we do sig figs in calculations, we line up the numbers, okay? Now there's different rules though for addition and subtraction versus multiplication and division. So we line up the numbers and round according to the number with the least number of decimal places, only when we're adding and subtracting. So for example, 3.35 has 2 decimal places, 1.6 has 1 decimal place. So when we do the math, our answer will only have 1 decimal place. So our answer in regards to this is 1.75, but we want to do this correctly in terms of sig figs. So our answer would be 1.8, and we want to make sure we keep our units, which is liters. So I like to do the math on the calculator, and then I like to round to the correct number of sig figs. The next one is multiplication and division. Use your numbers with the least number of sig figs. So this addition and subtraction was least number of decimal places. This is least number of sig figs. Okay? So let's do these 2 examples here, or actually 3. 190.6 times 2.3. Now, the entire time in my course, you will be allowed to use a calculator. So please don't hesitate to have your calculators, not your phone, but a scientific calculator. Costs about $10 to do your homework and to take your exams. Okay, so when I do 190.6 times 2.3, I get 438.4. Now, to count the number of sig figs in your total answer, you want to see how many there are here. There are 4 sig figs here. There are 2 sig figs here. Therefore, my answer is going to have 2 sig figs. So I round this number to 2 significant figures, which makes it 440. No decimal point. 2 sig figs. This 0 is not significant. Let's do one across the way. 3.145 divided by 1.59. This has 4 sig figs, this has 3 sig figs. My answer is going to have 3 significant figures in it. I do the division and I get 1.98. Remember not to cut answers off. You round. You look next to it. If it's a 5 and above, you round up. You round down if it's below 5. Okay? All right, this last one here is 0.6238 centimeters times 6.6. Again, there are 4 sig figs here. You do not count this 0 as a significant figure. There are 2 sig figs here, therefore the answer should have 2 sig figs. When I do the math here, I get 4.12. My answer needs 2 sig figs, so therefore my answer gets rounded to 4.1. Centimeters times centimeters is centimeters squared. Okay? All right, last step here is multiple step. What if you have addition and subtraction, multiplication and division all in the same problem? You take it step by step, okay? So when I see this problem, I'm going to solve this step first. I'm going to then multiply here, and then I'm going to divide. So I went ahead and separated those into those 3 steps. Get rid of that. So the first thing I did is 13.59 plus 1.1, okay? When I do that, I go ahead and get 14.69, but before I use that, I want to round. So this is the addition rule, therefore this has 1 decimal place, so this actually ends up being 14.7. Now I'm going to do that 14.7 times that 6.3, okay? When I do those together, I'm going to get 92.61. But again, we have to look at sig figs because it's being multiplied. This has 2 sig figs. This has 3 sig figs. So my answer is going to have 2 significant figures. So I'm going to actually round this to 93. So the whole top, or numerator, answer is 93. And then I'm going to go ahead and divide it by 12.2. Again, sig fig rule, least amount. My answer is 7.6 to finish that off. So do each step and do the significant figures for each step. Okay, do not wait to the end. All right, metric system. So metric system is probably one of the more difficult things that you'll have to utilize, but it is one of the most important. Okay, this is something you can actually use in your everyday life. Now, there are a lot of metric system units, but you only have to know the ones that are either red, shown on this side, or the ones that are blue on this side. You can see that I actually crossed out that hecto. You do not need to know hecto. So you need to know centi, milli, micro, nano, pico, kilo, mega, giga, tera, okay? Now, you also have to know the symbol. So C is centi, M is milli. This is called a mu because there's so many M's, so that like backwards U is mu, and for nano, P for pico, and then K, big M, giga, and big T for tera. Okay, so you do have to know the values, the symbols, and the actual prefix. All right, now, international system of units. So this is what everyone in the world, most of the world actually, except us, of course, uses, okay? But when you're in the science world, you have to use this because papers are being exchanged between all parts of the world. So lengths, System International is actually going to be meter. And the symbol for meter is a lowercase m, not to be confused with milli. It's meter. Mass is actually kilogram. Gram is actually really, really small. So if we use gram, it's too small. Everything has to be really, really big. So that is kg. Time is in units of seconds. Things happen very quickly in nature and during reaction. So minute is too long. And the way we write that is usually just SEC. Temperature is actually in Kelvin. Kelvin is a large K. Current is ampere. And we write that as amps. You've probably heard of that. And then one you may not have heard of if you haven't taken chemistry in a while is the amount of substance, which is a mole. And we will be very familiar with the mole. We write that by writing MOL. And we're actually going to not do the US units because we're not focusing on those in this class. Now, a very important thing that you're going to learn is dimensional analysis. We call dimensional analysis the factor label method. This is a way to get from one thing to another in a very logical and easy to understand fashion. Okay, but to do this, you have to memorize the metric conversions. Okay, so what we're going to look at here is the different amounts of steps. So, for example, when we are looking at a single step problem, you start with your, ignore this, I'm not sure where that came from, given units, and I will of course demonstrate this. And then you always take your given units and you put them at the bottom. And you put your desired, or what you're trying to get to, on the top. Okay? Anything on the top is multiplied, anything on the bottom is divided. And you can even look at this as two fractions. So multiply on the top, divide on the bottom. Therefore, you get your answer. All right, multiple steps, very similar. You always start with your given unit. You always take your given unit and you put it on the bottom of the first one. And you're going to go to an intermediate, which I, of course, will demonstrate. You then go from your anything on the top goes right back on the bottom again. That says intermediate. And you're going to go to your desired. Sometimes it's a little more complicated to look at it in this term in regards compared to just looking at an example, which I will show you right on this next slide. All right, so unit conversions, dimensional analysis, factor label method, any of those. So we're going to go ahead and start with 215 centimeters. Start with what you are given. Draw your first fraction bar. Take your units and put them right on the bottom. Don't even think about it. Not numbers, units. Centimeters and what I'm going to on the top. Desired on the top, what you're given on the bottom. Then fill in your numbers. 1 meter has 100 centimeters. Okay? Then you're going to go ahead, and since this is on the bottom, you're going to divide. So 215 divided by 100 gets you 2.15. And no answer in chemistry is complete without a unit. Okay? Let's do another one. 25 grams. Take the unit of grams and put it on the bottom. Take the unit you're going to and put it on the top. Use your memorized metric units and fill in the numbers. So 1 gram has 1,000 milligrams. Since 25 and 1,000 are both on the same spot on the top, you multiply them. So therefore, you're left with 25,000 milligrams. Again, you will lose points if you do not show work and if you do not have units. Okay, so make sure all answers in chemistry involve units and work. All right, 3.56 liters to milliliters. You take the unit you start with, you put it on the bottom. The unit you're going to on the top, 1,000 milliliters, to 1 liter. Go ahead and multiply because they're both on the top. You end with 3,560 milliliters. Okay, now conversion factors are factors that you do not have to memorize. The only ones you have to memorize are the ones that are metric. So I will give you, or your data sheet, which is located in the back of your recitation packet, has some given to you. Okay, so make sure you reference there. I did give you 2 right here to help us.
Alter, could you please call 1011? Thank you.
Sorry about the interruption. Okay, so convert 50 inches to feet. So go ahead and do the same thing. Start with 50 inches. Put your unit on the bottom and your what you're trying to go to on the top. There are 12 inches in 1 foot. I'm going to do the same thing here. Inches, what you're given, what you're going to. And then you're going to fill in your numbers. 12 with the word inches, 1 with foot. 1 inch, 2.54 centimeters. And again, these are ones you don't need to memorize. You probably do know a lot of these, but you don't need to. Okay? Now, this 50 and the 12 are on opposite ends, a top and a bottom, so you divide them. You end up getting 4.17 feet. And this is 11.1 times 2.54. You get 28.2 centimeters. Okay? A couple more examples here. 2.05 feet to centimeters. Take the unit you're given, put it on the bottom, what you're going to on the top. excuse me, this actually, we need to, let me go back here. We can't go directly from feet to centimeters. We need to go from feet to inches. So this is our first one where we're going to use an intermediate. So because I'm only given inches to centimeters, I need to get to one of these to get to the end unit. So I'm going to go feet to inches. 1 foot is 12 inches. And I'm also going to go inches to centimeters. So 1 inch is 2.54 centimeters. Okay? So the same math takes, you do the same thing. 2.05 times 12 times 2.54 centimeters gets you 62.5 centimeters. Okay? You always finish your unit with the thing that's on the top. All right, one more. 1 pound. I'm going to label that as LB. A pound. And I cannot go straight to milligrams, but I can go to grams. So 1 pound is 453.6 grams. Grams to milligrams is a metric unit conversion. These are both on the top. I'm going to, again, multiply both of these, and I'm going to get a very large number, 45360. Now, if you prefer to put these in scientific notation, perfect, no problem. Scientific or non, perfectly fine, unless it specifies in the directions. All right, a little bit more here. We're looking at percentages. Remember, a percentage is a part over a whole times 100. So for example, if we're looking at an experiment that has 28 red flowers, 41 white, and 12 yellow, we have to calculate the percentage of each flower, and we want to do 2 decimal places there. So the first thing I'm going to do is always do the total amount. So what I'm going to do is add everything up. 28 plus 41 plus 12. When I add those up, I get 81 total flowers. So that is going to be that bottom part of my fraction bar. And then I'm going to do it for the red flowers, the white flowers, the yellow flowers. And 81 is the same for all of them on the bottom. And then the part is which one we're referring to. So in regards to the red, it is 28. The white is 41. The yellow is 12. And you multiply by 100. Now, when I did my answers, I accidentally only did 1 decimal place, so please excuse me. When you do it yourself, please add a second decimal and make sure to round. So I'm just going to give you the answers that I've pre-calculated here. 34.6%. Again, please add 1 more decimal place to these. 50.6% and 14.8%. Okay? Not too hard. All right, now let's do it in terms of chemistry. So we have nickel oxide, 7 grams of nickel, 3.82 grams of oxygen. Calculate the percent of each element, 2 places past the decimal point. So I'm going to do the same thing. I'm going to get my total. I'm going to add up my 7 grams plus my 3.82 grams. And I'm going to get 10.82 grams. I'm going to do it for my nickel and my oxygen. 7 grams divided by my total times 100. My oxygen is 3.82 divided by 10.82 times 100. I get 64.70%. I did do 2 decimal places there, and 35.30% for the oxygen. Okay? All right. Now we're going to look at temperature, and we'll finish with density. So our temperature here, you are given these equations on your data sheet. So the Fahrenheit is the F, the C is the Celsius, and the K is the Kelvin. The equation for Kelvin, for some reason, is not shown here. I will write that. Kelvin equals degrees Celsius plus 273.15, and again, you will be given that. Okay? Now, you must also, though, be able to solve for Celsius. Okay, so let's go ahead and practice solving for a different variable in a formula. So when I'm given F equals 1 degree F, 0.8 times degrees Celsius plus 32, the first thing I'm going to do is subtract 32 from both sides. F minus 32 equals 1.8 times degrees Celsius. Now I'm going to divide both sides by degrees Celsius. Cancel those out. So my rearranged equation, which you will have to know how to do if you prefer to do it this way, is excuse me. I think I'm losing my mind here. Please excuse me and let me. You're probably looking at me thinking, what is she doing? Go back to this step. I would like the C by itself, so I'm actually going to divide both sides by 1.8. Excuse me there. Okay. So I had to divide the 1.8 because I want the C by itself. I just wasn't thinking there. So my finalized formula is F minus 32 divided by 1.8 equals degrees Celsius. So that is the rearranged equation. Okay. So let's go ahead and solve. So we have 800 degrees Celsius. We want that in Fahrenheit and Kelvin. So we're going to use both equations here. So my first equation I'm going to do is Kelvin equals degrees Celsius plus 273.15. So Kelvin equals my degrees Celsius. In this case, it is 800 plus 273.15. That's a pretty easy one. Kelvin does not have a little degree symbol. Just a little heads up. Excuse me. So it ends up being 1073.15 Kelvin, okay? And then we're also going to convert this 800 degrees to Fahrenheit, so I'm going to use the equation Fahrenheit equals 1.8 times degrees Celsius plus 32. And then I'm going to plug in the 800 degrees for the Celsius. I'm going to do 1.8 times 800, get an answer, add 32, and I get 1472 degrees Fahrenheit. Okay. All right, last step here is density. Our density equation is very simple, and it is given to you density equals mass over volume. Traditionally, mass is given in grams. Volume is traditionally given in milliliters or centimeters cubed. In most of these cases, we'll be working with milliliters. Calculate the density of some material that has a mass, so that is giving me M, and occupies that much volume. So I'm going to go ahead and write my equation. So density equals 427 grams over 35.0 milliliters. A nice division there. Answer is 12.2. Don't forget units, grams per milliliter. Okay. Remember, water has a density of 1.0 gram per milliliter. So if it's larger than 1, it would sink. So this material would sink because it's larger than 1. If it was less than 1, it would float. All right. Another one is being able to solve for other variables. So for example, calculate the volume. So I'm looking for volume. It has this density and it has this mass. I like to always label my variables. You're going to notice me always doing that. So I'm going to write my equation. Density equals mass over volume. My density is 0.500 gram per milliliter. I'm looking for V, so I'm going to leave that as V. Now, to solve this is usually where students get a little tripped up. When you have something on the bottom, you have to get it out of the bottom. So you're going to multiply both sides by that variable. So it equals V times 0.500 equals 125 grams. Okay? You're going to divide both sides by 0.500, get your V by itself, and your volume ends up being 250 milliliters. Okay? So again, last slide, what must you know? So go ahead and look over that. If you have any questions, please don't hesitate to ask, send me an email, and refer to any other YouTube videos if you need any assistance.